Okay, this video is going to be about the second question in the final exam practice. This question is pretty long. It's really like, maybe like two or three questions, but okay. In this video, I just want to prove that in this situation, we're going to prove that R mod I is an integral domain. And really, I just want to get you started anyways. Okay, so what is R? It's the polynomial ring in two variables and coefficients in the real numbers. So like a typical element of R is like f of x, y, and what's an example? Maybe like I plus x squared plus x cubed y minus 15 thirds y cubed x or something like that, right? Um, we have combinations of y's and x's multiplied by real numbers added up. Okay, that's like typical element of R. And what's an element of R mod I? Well, it's these polynomials, but under the equivalence relation where, f equals g, if and only if f minus g is in this ideal, the one generated by 1 minus x squared minus y squared. Okay, and what is the thing we usually do? Well, what should we do? Well, you should give kind of the things in R mod I names. So we should say the first thing we do is we put little x to be the coset of big X mod I, in other words, like that, and put little y to be the coset of big Y mod I. Okay. And our first, what I want to focus on right now is, okay, so, in the end we have to prove that things in R mod I, R mod I does not have any zero divisors, but we need a way, like a kind of convenient way to represent the things in R mod I, and that's what I want to focus on in this video. So I have this claim. Every R in R mod I can be represented uniquely as what? Well, as R equals R0 of x plus R1 of x times y. So, and R0 and R1 are just going to be polynomials with real coefficients in x. Okay. So where R0 of x might be like R00 plus R10x plus Rn0 x to the n and things like that. Similarly for R1 of x, it might be like R01 plus R11x plus Rm1 x to the m or something. Right? So R and R0 and R1 are just involving only real numbers and x's, and so that's what we have. Okay, and the idea is that whenever you see a y squared, because you're working modulo I, whenever you see a y squared, you can just replace it by a 1 minus x squared. Okay. In other words, so we're using the following. We have y squared is equal to 1 minus x squared plus x squared plus y squared minus 1 Okay, so this is an element of I, so what that means is that y squared equals 1 minus x squared plus I. Now we're replacing big Y and big X by their cosets, mod I, we get little y squared equals 1 minus x squared in R mod I. Okay. So, okay. So going back up to our example, if we're working mod I, well, we can replace this y cubed by y times 1 minus x squared. Okay, and then that'll get rid of this y cubed, and we'll have like some x's, polynomial in x, plus y times polynomial in x. Okay. So using this procedure, so it is by replacing y squared with 1 minus x squared, we can see every r can be written as r0 of x plus r1 of x times y. And now the question is, can it be written uniquely that way? What this boils down to is that we have to show that to show uniqueness, we suppose that r0x plus r1x times y equals 0 in R mod I. Okay. Or in other words, if we have to show that r0 and r1 are both 0. Or in other words, if we replace the little x's by big x's, we have to show that if this happens, then r0 equals 0 and r1 equals 0. Okay, that's what we have to do to show uniqueness. Okay. Okay, so let's suppose this is true. That we have r0x plus r1x times y is this polynomial times some other polynomial. Okay, so we say for a contradiction, we'll use that symbol. Suppose r0 of x plus r1 of x times y equals 1 minus x squared minus y squared times f of xy okay, and we try and get some contradiction. Okay, but now let's view both sides as polynomials in y with coefficients in x. So this is a kind of like a trick, I guess. So just remember elements of this polynomial ring in two variables are really polynomials in y with coefficients that are also polynomials in x. Okay, so now the coefficients are not just real numbers, they're polynomials as well, but just in x. Okay, and as such, they have, we can look at kind of like the y degree. You know, the y degree is just the highest, kind of like the highest y term in a given expression. So so on this side, the y degree is 1 if R1 is non-zero. If R1 equals 0, then the y degree might be 0, or the y, if this entire expression is 0, then the y degree is undefined. Okay, so if R1 equals 0, okay, wait, so if R1 is not equal to 0, what happens? Then the degree of the left-hand side, I guess I should call this equation maybe like star. The degree of the left-hand side of star is 1. And what's the degree of the right-hand side? Well, it is something that's either at least 2 if f of xy is non-zero, or it's undefined if f of xy is 0. Okay, so the y degree, oh, I should put like a y. The y degree of the right-hand side of star is either greater than or equal to 2 if f is non-zero, or undefined if f equals 0. Okay. Now, if I'm looking at the left-hand side, the possible degrees are, it's 1 if R1 is non-zero, it's 0 if R1 is 0 and R0 is non-zero, and it's undefined if R0 and R1 are both 0. Okay, so, and how do we match that up with a y degree that's 2 or more, or undefined? Well, both sides have to be undefined. Okay, so let's just summarize. If R1 equals 0 and R0 is not equal to 0, the y degree of the left-hand side of star, the y degree is 0, and if both are 0, the y degree is undefined. Okay, and the only way for this to match up, the degree of the left-hand side to match up with the degree of the right-hand side, is if both sides are 0. Okay, so the only possibility is that f of xy and R0 and R1 are all 0, which proves the uniqueness of the expression. Okay, it proves that the only way for a polynomial like this to be in this ideal is if it's 0. In other words, if we have this equation in R mod I, then we have R0 and R1 are both 0. And that is enough to prove uniqueness. So that kind of is finishing our claim. So now that gives us something to work with. To work in R mod I, we just have to work with expressions like this. Okay. So this ends the proof of the claim. Okay. Okay, and in a different video we'll kind of continue from there, but the idea is that we want to show that R mod I is an integral domain. That means we want to show, like, take two elements of R mod I. We know they can be expressed like maybe A0 of x plus A1 of x times y. So you might consider, the plan would be to consider something like this times b0x plus b1x times y. Set that equal to 0. Multiply everything out. Replace, so you get like a y squared, which you replace by 1 minus x squared, and go from there. And the goal is to prove that either b0 equals b1 equals 0, or a0 equals a1 equals 0. And there's like cases and stuff like that. But the key, well, one of the key parts is that we have this unique, every element of R mod I has a unique expression like this. Okay, thank you for watching.